Good evening and welcome to Monday Night Calculus on a Thursday. My name is Curtis Brown. I'm super excited to be joining you here once again, talking a little bit about calculus. Tonight I've got Steve Kokoska and Tom Dick back once again to share their expertise. And Steve, I know you've written up some great problems for us. They've been posted in the chat, or sorry, not the chat, in the description of this YouTube live event. For the last couple of weeks. And just today, I uploaded the teacher's notes and your presentation, so folks can go in and download that PDF if they would like to follow along with you and with Tom and some of the things you guys explore. One more bit of housekeeping before I let Steve and Tom kind of take over. Actually, two bits of housekeeping. One is a heads up that our next Monday Night Calculus will be streaming actually on Tuesday, November 1st, instead of on Halloween night, October 31st. We figured we'd give you guys that night off to go and do some fun things. And then the second bit of housekeeping, I just want to call out, I met a person at Northwest Math Conference this last weekend. Thank you very much for your kind words. If you're watching this evening, I didn't catch your name, but if you're watching this evening and you want to drop us a note in the chat and let us know that that was you, we've got a little bit of a prize, a gift that we'd like to send you, and we'll see how things go. All right, so Steve and Tom, I'm really excited for this evening's content. Let's get started.
All right. Thank you very much, Curtis. Great to be back with you tonight. I thought that Chris Collinsworth was coming tonight, but I don't see him on the Zoom call yet. But
he let me know he was a little bit busy this evening.
A little bit busy. Okay.
Yeah, it was a tough call, but he had some other things on his docket.
All right. Well, tonight we're going to look at derivatives of inverse trig functions, and this is one of my favorite topics. I really do like this one. It allows us to use a lot of concepts, a lot of theory, a lot of ideas that we've learned prior to this to learn something new. And as usual, at the very beginning here, we're doing something a little bit different this year. We're giving you these skills and essential knowledge statements to align with the AP Calculus CED. We hope that this will help you prepare for class, maybe create some sort of log if you want, maybe help prepare a lesson plan. Down at the bottom of this page, and again, as usual, I'm going to start up by just reminding you to do tonight's topic, to work through tonight's topic. We might use some of these background ideas, for example, some differentiation rules. So we might use the differentiation rule for the sum or a difference or a product, or even the quotient rule. We might use the chain rule. So for example, if we have y equal f of g of x, how do you find the derivative y prime? Well, we start at the outside and we work our way in. So that's f prime of g of x times g prime of x. And we're especially going to use the idea of finding the derivative of a function that is defined implicitly. So this is just an example. We think of y here. We think of y as really a function of x. And so we take the derivative of both sides of this expression. When we take the derivative of this, we must think of that expression as a product. And so we need to use the product rule. And I'll remind you that when I did this, I used that notation y prime, but some people like to use dy dx, and that's fine. And if we've done everything correctly here in an expression like this, we can really think of this as one equation in one unknown. And the unknown is y prime, and so we would solve for y prime. All right, so cool. We may use some of those ideas. And usual, Curtis, I have several questions lined up. And I know there's a little bit of a delay, but I'm going to give you a couple of questions to ask people. And please chime in when you get some responses. So here's the goal. We want to see if we can find the derivative of each inverse trig function using implicit differentiation. And we'll assume that these functions are differentiable. And I'd kind of like to think about that in a little bit more general terms, maybe before I begin. How do I know whether or not an inverse function how do I know if a function's inverse is differentiable. Well, let's suppose f is a one-to-one differentiable function. Then it can be proved that its inverse function is also differentiable, except where the tangent line is vertical. So what does that mean? If I have a function that's one-to-one and differentiable, then it has to have an inverse, and its inverse is also differentiable, except where the tangent line is vertical. Holy Toledo, I got to parse that out a little bit more. First of all, I'm not going to do any sort of proof here. I know that's kind of a dirty word, but I wonder if anybody, Curtis, on tonight, if anybody in the chat could give me some sort of a graphical reason why, if f is one-to-one and differentiable, then f inverse must be differentiable. That's the first question. And then the second question is, I wonder if somebody can give me an example of this case, which is, let me see if I can parse that out a little bit better. So f is one-to-one and differentiable. So therefore, it has an inverse. And its inverse is differentiable, except it might have a vertical tangent line somewhere. I wonder if there's a relatively easy example of that. All right, so there's two questions out there, and let's start by
watching the chat, Steve.
Okay, let me know.
Watch the chat and see where there's an example that pops up here, because I'm sure someone's going to give you one.
Okay, good. Let me know. All right, so let's see if we can find the derivative of the arcsine function. So I'm going to go back just for a second or two and think about the definition of the arcsine. What does y equal the sine inverse of x really mean? Well, sine inverse of x is equal to I if and only if the sine of y is equal to x and y must be in that interval. Here's a third question. Jeepers. Why is, well, it sounds kind of funny, but why do we have to have y in that interval, I wonder? Well, the way we're going to do this is with implicit differentiation. And so what I'm going to do is I'm going to start with this expression. I'm going to think of y as a function of x, and I'm going to take the derivative of both sides. So the derivative of x is easy. That's just 1. What's the derivative of sine of y? Well, again, we sort of have to think of that as a composition function. We start at the outside and work our way in. The derivative of the sine is the cosine. The derivative of the unit function is, well, y prime, or I wrote it as dy dx. So from there, after using implicit differentiation, it's not that bad. We're just going to solve for dy dx. We divide both sides by cosine of y, and we're almost done. What we need to do is to somehow get that expression, get that back in terms of x. Well, let's think about this, and I'm actually going to do this in two different ways. And Tom, you may have to help me here a little bit, but I'm going to try this in two different ways. First of all, I know that the sine, pardon me, I know that y must be in that interval. And if that's true, think about the unit circle for a minute. That means that the cosine of y must be greater than or equal to 0. Think of y as an angle. Think of the unit circle. So where is that angle? And the cosine of y must be greater than or equal to 0. Okay. Now I'm going to use a trig identity, and I apologize for this one, Curtis. I skipped a step here. Cosine squared is 1 minus sine squared. I took the square root of both sides. And because I know that the cosine of y must be greater than or equal to 0, I really have the positive square root here. Cool. So now I have an expression for the cosine of y in terms of x. And so now I'm going to put this all together. dy dx is 1 over the cosine of y. I've got an expression for the cosine of y, and I'm done. I've just proved, okay, that the derivative of the arcsine is 1 divided by the square root of 1 minus x squared. Now, I'm going to show you another technique here to find this expression for the cosine of y, I guess because, well, this is the way that I learned it. what I often do is I draw a reference triangle. I'm going to scribble a little bit over here, Curtis. So I draw my reference triangle, and this is a right triangle. And I'm going to put in at least two sides here by going back here to the very, very beginning, where the sine of x, I believe, was equal, pardon me, the sine of y was equal to x. So I draw a right triangle, I put my angle over here, and I'm sorry I'm going to do this in a little bit more detail than is necessary, but I know that's x over 1. And in right triangle trigonometry, what's the sine of an angle? Well, let's see, it's the opposite over the hypotenuse. If there's some sneaky way to remember all of this stuff, that's the opposite over the hypotenuse. So I'm going to put in the opposite is x and the hypotenuse is 1. So now this side, I'll just call A for a second. It's unknown. But now I can use the Pythagorean theorem in order to find that side. So I know that a squared plus x squared is equal to 1 squared, or 1. I know that a squared is equal to 1 minus x squared. And I know that a is equal to 1 minus x squared. Now I have to think a little bit more. Is it positive or negative? Well, it's representing a length, of course, in my triangle, but in my problem, I have to think a little bit about this. Is it positive or negative? But because y is an angle between minus pi over 2 and pi over 2, it's positive. So, all right, now I've got that side. Let's see. What's the cosine of y? Well, let's see. In right triangle trigonometry, what is that? That's the adjacent over the hypotenuse. So that's just the square root of 1 minus x squared over 1, square root of 1 minus x squared, and I've got the same result as up above. So that's probably overkill. Sorry about that, Curtis. We beat that one into the ground, but certainly now we've got the derivative of the arcsine of x. I'm going to let Tom try a little bit here with technology, and then we'll come back and look at another one. Okay?
Sounds good.
Tom, all yours.
Okay. Let me try sharing my screen here. And you all can let me know. Does that look good?
Yep, looks good, Tom.
84 here. Okay.
Looks good.
Just going to graph sine of x here real quickly. That's the function you were looking at the inverse of. See, I don't think let's see. Let me go ahead and use good form and close the parentheses there.
There you go. There you go.
And then let's take a look at the graph. And in some of what Steve was saying, to have an inverse function, you've got to start with a function that's 1-to-1. And if we think about the regular sine function, it's not even close to being 1-to-1. It repeats values over and over and over again. It's periodic, so the same values repeat infinitely many times. So what does it really mean to do an inverse sine function? Well, we get around that. When the function's not 1-to-1, we can still get an inverse if we choose some subset of its domain. Focus on that. So we'll restrict the domain of sine to, so we have a piece of it that is 1-to-1, and then that's what we'll really find the inverse of. And that restriction on the domain showed up in what Steve was saying, because we're going to reverse the roles of x and y when we get the inverse. It is actually from minus pi over 2 to positive pi over 2. That's basically, we get one nice stretch of the sine function that's centered at the origin. And so I wanted to share with you a kind of a general technique you can use on a graphing calculator to graph inverse functions. And it also is a chance to handle that domain restriction at the same time. Now, it may seem a little peculiar, but what we're going to do is actually make use of the parametric graphing. So let's go ahead and see what's going on there. So I'm going to go ahead and just clear out my y equals. But I'm going to go to the mode and go down and change our graphing mode from function to parametric. Now, when I return to the y equals menu, now I've got this, we've got x and y both as functions of t. By the way, you can use parametric to graph any regular function. You can just make x 1t equal to just plain old t. And then we can make y1 be the sine of t.
Right.
Cool.
And I'm going to go to my window. And oh, it looks like I already had this set up. Notice that I've got minus pi over 2, positive pi over 2 as the stretch of t values that I'm going to use. Okay.
Yep.
So let's take a look at this graph. And there it is. There's just that piece of the sine graph. And this piece, with that restriction, it is 1-to-1. So we can actually find an inverse for this function. That's exactly what the inverse sine is. So how do we handle that? How can we graph that easily? Well, we're just going to reverse the roles of x and y. So for my second parametric here, I'm going to make the x equal to the sine of t. And I'll make the y equal to t.
Hey, Tom.
Yes.
One other thing you could do to be really demonstrative of the fact that you're switching x and the x's and y's, you could actually do x1 of t in y2 of t and do y1 of t in x2 of t. Does that make sense?
Exactly. Yeah. Yeah. And in general, we could have, if we referred to x2 of t as y1t,
right?
Then whenever you would change your y1, it would
then everything would change.
Set to go, ready to go. Yeah.
Right. You could kind of have a general form of this.
Right. Well, let's take a look at this graph here. And there it is. So that red graph is the graph of our inverse sine. And a lot of folks I know, they think about the symmetry of the graph of an inverse function with the original function. And just for fun here, let me go back to, I'm going to go ahead and graph an x3 and y3. I'm just going to make both of those t. And what that's going to give us is a graph of a piece of the line y equal x, because that's the line that those two graphs are reflected over. So that's kind of a nice general way to graph inverse functions. And in general, even if your function is not 1-to-1, you can use this technique. You'll get an inverse relation. For example, if I tried this with a regular sine function, my red graph would be periodic, but winding up and down the y-axis. And so it wouldn't be 1-to-1, but it would still have that reflection property. Okay.
Do one more thing.
Yeah, go ahead, Kurt.
Do one more thing for me, Tom.
Okay.
Let's look at the table.
All right. Be happy to do that. Let's
check out the table here. And I think this is a really powerful demonstration now of that inverse as well, right? So I've got my original function in blue here, and side by side, I can see x's and y flipped all the way.
They're just flipped around.
That reflection across the two. Now I know we constructed it that way, so it should make sense, but this is a nice visual to be able to see that happen directly across.
Now these values of t, several of them are actually kind of out of bounds for us, right? Because our values of t should be between minus pi over 2 and positive pi over 2.
Sure.
So when I just went to the table, it used its default settings and it's giving me these whole number values.
Right.
But we could, for example, put in say pi over 3 for a value of t, ask for that. And so this is our y1 is the sine of that.
Yeah.
That means on the graph of our inverse sine, For an x value of 0.866, we'll get a y value of 1.0472. So again,
That's fabulous.
reverse. Yeah. All right, I think I will turn it back over to Steve.
Okay.
And let me do a, let's see, I think this will, not a new share. Don't want to do that. Let's see, I just want to stop share. Interesting. Here we go. It's all right. I finally found it. Okay, it's all yours.
Okay.
Steve.
All righty. Thank you, Tom. Here we go. All right. Well, let's try another one. That was really cool. Let's see if we can get the derivative of the arctangent function, and we'll attack this in much the same way. So we'll start out with y equal to the arctangent function, and we want to find y prime or dy dx. And if that's true, then the tangent of y must be equal to x. You'll notice that I didn't put any domain over here, so that's something that one might think about or might become evident here as I draw a graph, but that's something that maybe we could think about. So I'm going to do the same thing. I'm going to take the derivative of both sides with respect to x, thinking of y as a function of x. The derivative of the tangent is the secant squared, times the derivative of the inner function, which is dy dx. And once again, the derivative on the right-hand side is just 1. Okay. I'm going to solve for dy dx. It's 1 divided by the secant squared. And now I'm going to make use of a trig identity. Secant squared is 1 plus the tangent squared. And son of a gun, I know that the tangent of y is equal to x. This one's maybe a little bit easier. There's the derivative of the arctangent of x. Pretty cool. And just to make sure that this is consistent with something I did a minute ago, I'm going to take a look at my reference triangle here. Let me make sure that this works. There's my angle y. All right, Curtis, I'm going to give it a shot. What's the tangent in right triangle trigonometry? Do you remember?
Adjacent over hypotenuse. No, hold on. Adjacent, opposite over adjacent.
There we go. The opposite over the adjacent. Okay, very good. So there's my x over 1.
It caught me while I was thinking about something else. I apologize.
That's okay. That's
it's like right. It's like being off task during class. I need to catch back up.
Focus, Curtis. Here we go.
Focus.
Here we go. So I'll call that hypotenuse C. So, okay, so let's see. That would be C squared. It's got to be equal to a squared 1 squared plus x squared. Okay. So C would be equal to, well, just the square root of 1 plus x squared. Okay. So let's see. What's the tangent? Pardon me. What's the, what do I have now here? The tangent of y we know is that. What do we need to find here? The secant, right? So the secant of y, let's see, 1 divided by the cosine of y, right? So let's see, what's the cosine here? Sorry, a lot of fractions in this one, Curtis. I apologize. The cosine of y.
Over hypotenuse.
There you go. That's the adjacent over the hypotenuse. So there we go. So that's 1 divided by the square root of 1 plus x squared, just to make sure all of this works. There we go. 1 plus x squared. And of course, I needed the secant squared, so it works out. Thank goodness. All right, so you know me, Tom, I like to do a little bit of graphs just to sort of, I don't know, confirm what I found here. And there's a nice question or two in this one too, Curtis, I think. One that we don't often ask, we often don't involve our BC teachers enough, but there's a good BC question in here, I think. So the blue curve, if you can see the color, is a graph of y equal to tangent inverse of x. There are 2 horizontal asymptotes. So I'll scribble a little bit in here, one of them at pi over 2 and another one at minus pi over 2. And let's see, we just found that the derivative of this function is 1 divided by 1 plus x squared. So the first question, or the first thing we might want to think about is, does this make sense? Well, this function y equal tangent inverse of x, as I've drawn it, seems to always be increasing. So its derivative should always be positive. That looks right. As we move left to right, it kind of looks like right here at 0 is where its steepest derivative might be. Okay, so that's the highest point on the graph of the derivative. That seems reasonable. As we keep moving left to right, as x increases without bound, this curve gets flatter and flatter. Its derivative gets smaller and smaller, closer to 0. So I'm feeling pretty good about this one. So here's the BC question, Curtis. Let's see if we can get an answer to this. You know, first of all, just as an aside, as I look at this green graph, it kind of looks like the graph of a normal curve. Those of you who teach AP stats, but it isn't. It's not the general form of a Gaussian or a bell-shaped curve, but it looks
familiar, doesn't it?
It looks familiar, doesn't it? It looks like it. So that makes me think about, you know, I'd kind of like to know the area under this curve from minus infinity to plus infinity. Well, all right, I'll make it a little bit easier. How about the area underneath that curve from 0 to infinity? 1 divided by 1 plus x squared dx. In this case, we can think of that region. We can think of that improper integral as representing the area of that region. And do any of our BC teachers know what that's equal to? Is it convergent? Is it divergent? If it converges, what's the answer? I think that's a good one. If you know that answer and you teach a little bit about AP stats, then you can actually recognize how to use this curve as a probability density function, which is very cool. I think there's a nice tie in there.
Yeah.
And for 25 bonus points,
25 bonus
25 TI bonus points, I think Tom will have to help me on this one, but this curve right here has a special name too, not a bell-shaped curve, but I think it has a special name. And with that, I'll turn it over to Tom for a little bit more technology.
All right, so 2 questions out to the crew on the chat.
I need an answer on that one.
We need an area underneath of the curve, or well, half the area underneath the curve.
Right. If it exists, it might not. That's not clear yet.
We haven't said it that it does.
Okay.
Right. And then we also need the name of that curve.
If it has a name, we want to know the name.
I want to know it. Come on, let us know you're in the chat here. I've been.
And it's not Billy or
I'm the only one
or
saying anything in the chat tonight, by the way.
Okay. All right, Tom. Sorry about that. All yours.
All right. Okay. I'm going to share a couple of different calculator screens, and let me start out by just going to TI-Nspire screen here.
Okay.
And I want to get my calculator. Let's go ahead and get to our F1 and our graphing thing. And I'm going to graph actually the inverse cotangent.
Okay.
So I'm just going to type in ARC. That's another name we can use as Arctangent. ARCCOT of X. And there we got a nice graph of that. Okay. But let's see. How would we graph that on the TI-84, I wonder? Because I don't think I have an inverse cotangent key. Let's see. Oh, let's tell you what. Let's do a new share. Let me go over to the 84. There's our table again. Let me go to y equals. Oh, we're still in the parametric here.
Yep.
We could use that, I suppose. But let's actually, let's see another way of getting the arc cotangent. Let me go back to mode, change back to function.
We just got an answer for the area underneath the curve, by the way.
All right. What is it?
All right. Let's
Well,
hear
Pi
it.
over 2
It is indeed pi over 2. Very good, which is absolutely amazing, isn't it?
from 0 to infinity.
From 0 to infinity. Absolutely amazing.
All right.
Wanda's up for 25 points here.
Oh, 25 bonus points.
We need the bonus points now, Wanda.
All right. Well, I'm going to actually try, let's see, what would happen if we did the inverse tangent of 1 divided by x? What would that do?
I don't know. Do tell.
Ah, interesting. Okay. So that's getting a graph that, let's see, I think on the Inspire, this piece here was actually lifted up.
Indeed it was.
One single piece.
Indeed it was.
Yeah. So that's a technique one can use effectively for inverse secant, inverse cosecant, but you got to be a little bit careful with the inverse cotangent. So
what is that, Tom? Using as the argument 1 over x?
1 over x, thinking, okay, if my x is the result, since cotangent would be adjacent over opposite,
Gotcha.
if I flip that over and take the inverse tangent, it should give me the same thing. But you can see that we've got to be a little bit careful there. So we'd have to use some kind of a split define function here.
So is there any way to trick the calculator to do this, to make it look like the other one by, for example, using an absolute value for x? Is that what's following this up, or not following it up, but is that a way to get around it, or?
Well, I think actually what we would end up needing to do is actually adding pi over 2
Yeah.
Okay.
to this part of the graph. Or no, actually we would add pi,
Right.
excuse me. And so if we did a split define function,
Okay.
then we could get that graph of the inverse cotangent there.
Okay.
All right. Now, what I'm going to do, though, is I'm going to go ahead and change this to regular inverse tangent of x, the same one that you were looking at.
Okay.
And just illustrate something I'd like to do with my students whenever we're encountering a new function and trying to think of the derivative. So let me go ahead and graph this inverse tangent.
Okay.
There we go. Graph similar to yours. And before we even try to plot a derivative, I just ask my students, well, can you see some points that would have to be on the graph or be close to being on the graph of the derivative of this function? And have them think about first principles would be, we're trying to measure the slope of the graph of this. And a zoom decimal window is really good for that because you're going to have equal scale for x and y, so you can judge the slope looking at it here. And if we just wanted to plot a few points as guesses here, what we might want to use is the draw menu. And so let me pull that up here. Let's see, our draw menu is right here. And we're going to plot some points. So I've gone over the points. And a point on, that's the one we want. Let me just do a 1. And now what I can do is move my cursor over. And if I hit enter, it'll plot a point for me. So I'm going to go over here to this part of the graph. And I'm looking down here and I'm seeing, wow, this is really, really flat. It's almost horizontal. So the slope is pretty close to 0 here. So let me plot a y value of 0 here. So I'm just going to hit enter, and it should leave a point right on the axis there.
Okay.
Now let me move over here. Whoops, so a little bit too far. Let me move around here close to -1. And here the slope looks like, well, if I just kind of think of a tangent line, yeah, I don't know. It looks like about a slope of, looks like a run of 2, a rise of 1. I'm going to say it's about a slope of 1/2. So let me go up to a y value of 1/2. And let me plot another point. And then if I go over to 0, that's where my curve is the steepest, but it looks like, almost looks like y equal x here. So it almost looks like a slope of 1. So I'm going to plot a y value of 1. Hit enter. And now it's going, let's see, it's getting less steep. So let me go here and put another value of about y equals 1/2, because the slope looks like about 1/2 there. And finally, it looks like it's getting almost horizontal again. So way out here, the slope is almost 0. I'll just go ahead and plot 0 here. And these are points that I would think would be on the graph of the derivative of this function. So let's see how good a job we did. I'm going to go back to y equals, and I'll go to the math menu. Let's do number 8, which is the numerical derivative. We'll take the derivative with respect to x of our y1. And we're graphing this as a function. So I'll just put x equal x. So it's going to do that for each x value across the screen. So let's see how our derivative looks like.
While that's plotting, Tom, and that looks beautiful. Nicely done, by the way. Nicely done. I did get a question from Wanda about the inverse cotangent graph that you had just a minute ago. The difference between graphs, does it have to do with the principal values of that?
Yes, exactly.
Function,
yeah.
Right. And do the principal are the principal values universal then? Value intervals. Sorry, the principal value intervals universal.
Wow, that's a great question, because the graph that we had where it was broken into 2 pieces, that was a legitimate inverse for a part of the tangent graph, because it was nice, it was 1-to-1 and everything. The problem was it was not continuous.
Right.
And so the convention is to choose a stretch of values. I think it's from 0 to pi. So you'll get one nice continuous piece of the cotangent curve. So when you reflect it over the line of y equal x, you get a nice continuous piece. And so that's why that choice is made. But whether it's universal, I don't know if there are times when folks make a different choice. For example, when you do the inverse secant, it is broken into 2 pieces, I believe.
Right.
Yeah, but that's a good question. Yeah, I don't know if other choices are made depending on the application you might want to actually use.
I would think, yeah, you would choose depending upon how you're going to use the function.
So some convention is made for the graph of the cotangent, inverse cotangent function. There has to be, so that we all have an agreement on what that's going to look like. So, neat question. Okay. I'm going to do one last graph here and turn it over to Steve, and that is, this was a numerical derivative, but Steve derived this 1 over the quantity 1 plus x squared. Let's go ahead and graph that too. That would be supposedly the exact derivative. Let's see what the graph of that looks like. Supposedly. Oh, there it is again.
How about that?
But this visual estimation of slope values, I think that's just a really good exercise. Every new function we hit, let's just try to sketch a few points what we think are on the graph of the derivative, And then as we derive the actual derivative, check out, see how good our eyeballs were. So,
the way you did that in Y2, it's pretty generalizable again.
Exactly.
Right?
Yeah,
So
you can use that over and
go
over.
back and change your Y1 and then do this same exercise repeatedly with different functions.
Exactly. We could change our Y1 here. The Y2 is all ready to go. The derivative.
Yep.
And then we could try out, if we did some derivation, we could check it against the numerical derivative. They should be fairly close. Yeah.
That's a great exercise. I love that as a calculator exercise to kind of get my eye working. Okay. Yeah, that's really nice.
So Tom, just for the heck of it.
Yeah.
So since the 84 does not have an inverse cotangent, go back into that argument of the tangent inverse and make that a 1 over x.
Okay.
And let's just see what it gives us for the inverse cotangent derivative. And maybe there's a relationship here.
We may need to turn off your...
I'm going to turn off Y3 because...
Turn off Y3 would be fine, yeah.
Okay, let me just clear it and let's graph it.
Let's see what that gives us. Huh. I wonder what the relationship is between that red curve, the derivative of the cotangent inverse, and the one we just found.
Yeah. It's a nice point. It looks like it's that bell curve upside down.
Upside down, isn't it? Huh?
Yeah. Really nice, Steve.
Very cool.
And this would be the graph of the inverse cotangent, except for at x equals 0.
0, right. Yeah.
Because to get the actual cotangent inverse graph, we would just be lifting this piece up by a value of pi. But since we're just adding a constant, it'll have the same slopes.
Have the same
except
derivative.
where we broke it, where it was broken and not continuous, it won't be differentiable. And if we actually traced the derivative graph, and that's right, this is a numerical derivative. Notice it's giving us this really large value. So it's actually doing a difference quotient, but the actual derivative is not defined at x equals 0 for this function. But the actual cotangent, the slope there will be -1. All right. I'll do a stop share.
Very cool.
And turn it back over to you, Steve.
All righty. Thank you. Here we go. Curtis, here's what I'm going to try. Since we have two nice derivatives of inverse trig functions, I'm going to do a couple of examples, do a little bit of generalization, and then we'll get to some of the problems anyway that we posted, if that's okay.
I think that's a great idea.
All right.
15 minutes, Steve.
Okay. So let's see if we can differentiate each function. You know, we have a lot of calculus tools here, a lot of ways to take derivatives. Let's see what we can do with these functions. Oh, man. So I'm going to rewrite this first one. There's a lot of -1s in this one, and they mean different things. I like this. You know, in AP Calculus now, we're talking an awful lot about notational fluency and, of course, communication. But we want students to use correct notation. So how do we get the derivative of that? Well, we start at the outermost function. The outermost function is actually this exponent. So we take the derivative of this outermost function. It's -1 times what's inside those parentheses raised to the -2 power times the derivative of the inner function. So I put in an extra step here, I think, just for clarity. And let's see, the derivative of that inner function is 1 divided by 1 plus x squared, as we just learned. And I just did a little bit of simplification to write it like this. Not content with that, I want to take a look at the graphs here. I want to make sure that everything makes a little bit of sense. As usual, my blue curve here is my original function. And you know, I got to think a little bit about this too. Maybe this is another question out there, Curtis. I wonder what the domain of this original function is here. The one in blue, 1 divided by the tangent inverse of x. It's a little given away, or at least there's a hint in the graph here, but maybe we could think a little bit about that. And a graph of the derivative, the way that I did this, the way that I produced this graph, was not with n deriv, but rather I actually plugged that function in and graphed it. And does it make sense here? Well, let's see, to the left of 0, the function, the blue function, is always decreasing. So the derivative better always be negative, and it sure looks like the slope of the tangent line is getting bigger and bigger negative as we get closer to 0. So I feel pretty good about that. To the right of 0, oddly, strangely, it is also always decreasing. The green curve is always negative. Good. As x increases without bound, the slope is getting closer to 0. I like that. I feel pretty good about that answer. That graph sort of backs that up. Good. The next one's kind of interesting too, I think. You know, I'm going to, oops, I'm sorry about that, Curtis. I'm going to try to scribble a little bit here just to remind myself. I think the original function was this: x times the sine inverse of the square root of x. Holy Toledo. It almost looks like, heaven forbid, the product of 3 functions, but it isn't. That square root of x is actually the argument on the sine inverse. So I have to use the product rule. The derivative of the first derivative of x is 1. Leave the second function alone. Plus the first function times the derivative of the second. How do I do that? Well, let's see. You know, sometimes when I finish all of this in my class, I write the derivative of my inverse trig functions in terms of u, thinking of this as a very general function u in terms of x. So this is 1 divided by the square root of 1 minus u squared, so square root of x squared, times the derivative of the inner function, 1/2 x to the minus 1/2. Don't let me make a mistake on this one, Curtis. I tried to do a little bit of simplification here. So there's the 2 in the denominator, and this is really 1 over, see if I've got this right, 1 over the square root of x. So there's a little bit of canceling with that x, so I've got a square root of x up there in the numerator, 2 times the square root of 1 minus x in the denominator. Not very pretty, but darn it, there's the derivative. And this is a cool problem. Look at the graph of these two. The blue curve is a graph of my original function. Remember, x times the sine inverse of the square root of x. And the green function is a graph of its derivative. So one of the first things, again, we might think about is what's the domain here of f? Boy, I'd like to get a couple of answers here in the chat. What's the domain of f? It doesn't look like I've drawn anything beyond certain points here on my graph, but I'm wondering if I only took a look at a piece here. What's the domain of f? And another thing you might think about here is, well, I drew this blue curve with 2 dots here, 2 solid dots, but I also drew in this dashed vertical line, which seems to suggest that there is a vertical asymptote, and in fact, a vertical asymptote on the derivative. So I wonder if anybody can reconcile that for me. Is there really a vertical asymptote there? And if so, how do you sort of resolve that? Does the graph make sense? Can you see from the graph? Or can you give me a little bit more detail in this graph that indeed suggests I have a vertical asymptote there? Wow, there's a lot of cool stuff going on here.
There is a lot of good stuff in that question there. I think I'm going to need a second to think about that.
Okay.
I mean, I know you've got a square root of the sine, 0 to 1 for the domain, including 0.
I believe that is true.
What Wanda?
So I believe that is the domain of f. How do you get that?
Parenthesis on the 1. Parenthesis on the 1.
Parenthesis on the 1.
Yeah,
I don't know if I'm looking for the domain of f. Here's f. Can I plug in an x equals 0 in there?
Yeah.
I think so.
Yeah. Yeah, I guess you
Find
can.
the sine inverse of 0. So
Yeah,
I
sine
think
inverse of 0. So I think we're okay.
I think we're okay. And can you look at that graph and sort of reconcile that vertical asymptote? I mean, it might not be too evident, but can you kind of explain what's going on right here?
We
So x equal 1 is in the domain of f. So I can actually find the value of
yeah.
1 times the sine inverse of the square root of 1, which is 1. I can actually find that value. And in fact, somebody can tell me what that value is. Boy, there's another question.
The limit of the denominator, square root of 1 minus x as it approaches 1 does go to 0, which I agree with.
I agree with that.
Which would shoot that up. That would shoot the value that you're adding toward positive infinity, right? Because you're adding a 1 over a value that's going close to 0. So you're adding a value that's going to go to positive infinity, right?
Yeah, very good. So that's an analytical argument, and that's a good one.
I still don't have a nice graphical argument.
Well, here's what I think is happening. Tom, correct me if I'm wrong. It's hard to see, but as this graph
Can we
comes,
zoom in?
I'm awfully sorry. Tom might be able to do that. As you get closer and closer to x equal 1, this graph here is getting very, very steep very quickly. And so as it gets steep there and I draw tangent lines, those tangent lines have slopes that are getting very, very large. And that's why this derivative increases without bound graphically. There's a graphical argument in there.
If we zoom in, the slope is approaching vertical. That's what Mark is
As we
suggesting
zoom
here.
in, the slope of the tangent line is getting bigger and bigger, is increasing without bound.
It's
That's
it's
correct.
increasing without bound.
Yep. Yeah,
Okay.
that's kind of cool.
Yeah, that's what Wanda, we're getting a few comments now about approaching a vertical tangent line.
Very cool. Very good.
Or yeah.
All right, so I'm not going to do any of the other inverse trig functions in gory detail. Here's a table of them. We did this one tonight. We did that one. And I think given what we have done, I think that you could now do in your class, you could have your students figure out the other remaining derivatives. You will notice that there are some nice relationships here between the derivative of an inverse trig and sort of its co-function. So the derivative of the inverse cosine is the same except for this minus sign. And we discovered this one graphically. Look at the derivative of the inverse cotangent. That's got a minus sign in there compared to that function. And here's the derivative of the, whoops, I'm sorry about that, Curtis.
It's all
Here's
right.
the derivative of the inverse, oh shucks. Here's the derivative of the inverse secant and the inverse cosecant, and they differ by a minus sign also. So very good. With that table in hand, with that table in my toolbox, I'm going to take a look at least a couple of the problems that we assigned, that we gave for homework here. So we'll put all of this together and see if we can get a couple of derivatives. I still like to see my students do some of this stuff by hand. Okay. College profs still like to see their students do some of this by hand. How do we find the derivative of the cosine inverse of 1 over x squared? So this is my argument. This would be minus 1 divided by the square root of 1 minus that argument squared. So 1 over x to the 4th times the derivative of the inner function. Well, really that argument is x to the minus 2. So the derivative of that is minus 2x to the minus 3. And then I'm just going to try to do a little bit of simplification. I got a common denominator inside this square root. And let's see. There's my x cubed in the denominator. There's my 2. I had a couple of minus signs that canceled. And I think what I did is I took this x squared, this x to the fourth through the square root symbol as an x squared, did a little bit of canceling, and I think there's my final answer. I didn't add any graphs in here, but I think, Curtis, a good exercise, a good thing for students to do is to graph the original function and to graph their symbolic derivative and to make sure that they make sense. Here's another nice one.
That's a really nice graphical exercise.
I think it is. I think it is. X squared times the secant inverse of x to the fourth. I have to use the product rule. Okay, good practice. The derivative of the first one is 2x. Leave the second expression alone. Plus the first expression, derivative of the second one. Well, all right, thinking back to my table here, it's 1 divided by the argument times the square root of the argument squared times the derivative of the inner function. And sparing you a little bit of gory detail, I did a little bit of simplification for that one. That's kind of cool. And here's a good one. This was typical of my college professor, college calc professor. He used to love these composition functions with things like this. The tangent inverse of the sine inverse of x. What's the outermost function? Well, it's the inverse tangent. So the derivative of that is 1 divided by 1 plus the argument squared, be careful with the notation, times the derivative of the inner function, which is this sine inverse, 1 divided by the square root of 1 minus x squared. And I just did a little bit of simplification here, just to write that as sort of one prettier fraction. And I think there was a part D in the problems that we assigned, and I apologize for this one, Curtis, but boy, I really like this one. And one of the reasons that I put this in here, seriously, Curtis, is, and I think Tom will back me up on this, the AP exam recently has included a lot of problems, has included a problem or two in the free response with an extra parameter of 2. We've seen A's and B's and M's and K's pop up. So I think it's a good idea to have your students work with some of these expressions that have extra variables in them. So I won't go through this one in gory detail, but the outermost function is the cosine inverse. The inner function is actually a quotient, so we've got to use the quotient rule. I think there's a trig identity or two that I used in here, and son of a gun, this simplified to this expression. So you might ask your students if they tried this problem that was posted, if they got that one. I'm going to look at one more, Curtis, but I'm going to skip one here. I'm actually going to look at number 3 because this is one of my favorites. Let's take a look at the graph of the sine inverse of x plus the cosine inverse of x. So I sketched the graph of this in an appropriate viewing window, and I was kind of surprised, and your students might be if they do this. I got a horizontal line segment, which is crazy. How can that be? So what I'm going to try to do here in part B is to write an equivalent expression for f of x that doesn't include any inverse trig functions.
This was on Mark Crowley's test this week, by the way.
It was. Holy Toledo. Did anybody get it right, I wonder?
I don't know. They may be watching this to figure out.
Well, let's see. We know that for any angle theta, we actually have a trig identity that says the sine of theta is equal to the cosine of pi over 2 minus theta, which is equal to x, for x between -1 and +1. That is true for any angle theta. So that means that theta must be equal to the sine inverse of x, and pi over 2 minus theta must be equal to the cosine inverse of x. So, son of a gun, if we want to add these two expressions together, that's just adding theta plus pi over 2 minus theta, and we get a constant, pi over 2. And son of a gun, if you come back up here and look at that graph, that's where that horizontal line segment is at y equal to pi over 2. And finally, down here in part C, well, wait a minute. What would happen if we took the derivative of those two expressions? The easier one, I think, is, of course, if we have the derivative, or pardon me, if we have a constant function, we know the derivative of any constant function is just plain 0. But if we take the derivative of this original one, the derivative of the sine inverse was this, the derivative of the cosine inverse was, wait a minute, the same thing except the opposite. If we add those two together, we do indeed get 0. That's kind of a neat problem, I think. And we'll post, of course, all these answers on the website. Tom, did you have any one last technology tip here, or are we good?
No, I think we're good, Steve. So.
Okay, excellent. Well, thank you, Curtis.
Yeah,
Nice
I
work.
think this was really nice. Wanda pointed out f of x being the sum of the complementary angles. And Mark said that his students groaned when they saw the key.
Saw the answer.
Some of them got it right, but it wasn't the elegant way.
Okay.
That's the way that it worked. So yeah, it was a great session this evening. Good stuff in there, Steve. Some really nice problems, some good demonstrations. Tom, on the technology, I really liked those things. Those were nice. Couple of things, just a really quick wrap up here. If you are watching these sessions, and you have been watching these sessions, I've got little professional development certificates that you can download. If you just email me, I'll put my email here in the chat in just a second to make sure you can email me, and I'll get you the link for that professional development certificate. And secondly, be watching these videos for the teacher notes. I'll make sure that those get put up. I put the link to 2 weeks from now chat, or in the chat, so you can go over there, click on that, and be watching really soon. We'll make sure that those problems get up there so that you can download them. Steve's got those written, I think, or almost has them written.
They're done.
He'll send them to
Tom's
me very
looking at
shortly.
Yep.
And then we'll have those up there for you so you can start planning your next activities around this. Again, I encourage you to have your students join us, ask questions and things in the chat. We certainly want to be able to be accessible to both teachers and students. And so thank you for joining us. Have a great evening, and we'll look forward to seeing you on November 1st. Remember, it's Monday Night Calculus on a Tuesday in 2 weeks. All right, good night.
Thanks, Curtis.